So today we're discussing titration, and specifically we're going to address the stoichiometry behind a titration experiment, some of the general types of titration experiments that you can use to establish the concentration of an analyte, and we'll talk about the use of standardization in titration experiments that are designed for the analytical chemistry laboratory. We're going to spend a little bit more time next Monday on titration as well. Well, we'll be addressing direct titrations today. We will talk a little bit about back titrations on Monday. Specifically today, we are going to address how you determine the concentration of an unknown acid or base generally based on your titration data. We'll talk about why primary standards are needed in a typical titration assay, and we'll do some worked examples that revolve around using titration data to find an analyte concentration, and how you use titration data to standardize a solution of titrant prior to running your titration assay. Your assigned reading is from late in Chapter 6 related to titration, sections 6.5 through 6.7 in Harris, early Chapter 7, sections 7.1 through 7.3, which deal specifically with titrations of different kinds. And you'll want to refresh yourself or reintroduce yourself to some key vocabulary terms related to titration, specifically concepts of titrants, indicators, the difference between equivalence point and endpoint, which we'll cover in more detail today, and how this leads to an unavoidable titration error. The first thing we want to discuss in detail today is how a titration experiment setup is used to directly reveal how many moles of a reagent are needed to react with the analyte, and how you can use the number of moles of the reagent, or what we're going to call the titrant, to determine the number of moles of the analyte in the original unknown based on a known balanced chemical equation. Just like gravimetric analysis, titrations are a classical group of wet chemistry methods for determining the concentration of an analyte. An experiment where you use an in-solution chemical reaction to determine an analyte's concentration is also called an assay in analytical chemistry circles. So if you hear me say assay and experiment involving a chemical reaction are interchangeable terms. Specifically, a titration is a type of assay where increments of a known reagent solution, which we would call the titrant, are added to a solution containing the analyte until the reaction between the analyte and the titrant is complete. So fundamentally, titrations and gravimetric analysis have a lot in common in that you're actually using the stoichiometry of a known balanced chemical equation to determine the number of moles of the analyte that are present in your unknown sample. The key difference between the methods is how we go about spotting when the chemical reaction is complete and all the moles of the analyte are used up. In a gravimetric analysis reaction, we know that once the precipitation reaction is complete, we have precipitated out all the moles of the analyte that were in the sample to begin with. A titration is not actually so different in that we're running a chemical reaction. We're trying to observe how many moles of the reagent that is in the titrant solution have to be added to use up the original analyte. And this is why I think titrations may seem a little obtuse to students when they're going into a chemistry lab and they're running titrations for the first time. Ultimately, with any titration, no matter how complex, all we want to know is how many mils of the titrant solution we had to add to use up the moles of the analyte that were present in the sample. And the rest of the titration setup, the use of the burette, the use of an indicator, or the use of a pH probe, are all about spotting how many moles of the titrant had to be added to the analyte to get a complete reaction. Ultimately, your titration comes down to a balanced chemical reaction and the stoichiometric relationship between the chemical species that's in the titrant solution and the chemical species that is the analyte. So I know many of you have run acid-base titrations before, and so we're going to use a straightforward example of a weak acid, strong base titration to illustrate the general strategy for setting up a titration reaction and how we use that to determine the moles of the analyte that were present in the original sample. So for instance, this net ionic equation represents the acid-base reaction That was the subject of the YouTube video that I pinned to the front of this lecture. I hope you took a few minutes to check out that YouTube video, even if you didn't see quite all the connections in that video yet, connections between standardization and titration. I'm hoping that because that video represents a full analytical procedure for doing a titration correctly, by the end of this lecture module, you'll be able to go back to that video and say, I see how all the pieces fit together. I understand why they're doing this step. I understand why they're doing that step. And at the end of our titration discussion on Monday, I'll have a little post-lecture exercise, which I hope will kind of drive those points home. But even though a titration looks complex on the outside, once again, it all comes down to stoichiometry and a balanced chemical equation. So the example we're going to talk about is a titration to determine the concentration of acetic acid, which is a weak acid, chemical formula C2H4O2. This is a monoprotic acid with only one ionizable proton, which is why I've moved the ionizable proton over here in the chemical formula. 1 mole of acetic acid reacts with 1 mole of a strong base, like hydroxide. And the products of the reaction are acetate and 1 mole of water. The goal of an acid-base titration experiment like this is generally to see how many moles of base we have to add to completely use up all of the acetic acid that we started with. By doing this, we determine the number of moles of acetic acid that were present in the original sample, and if we know the volume of the original sample quantitatively, we can calculate the concentration of acetic acid in the original sample with good accuracy. Now, why a titration is set up the way it is because when we actually just react acetic acid with a solution of sodium hydroxide, we're mixing a clear colorless solution with a clear colorless solution. And it's not obvious if you're mixing two clear colorless solutions and they make a colorless product and a colorless product with no precipitation or no obvious visible sign that a reaction is occurring. It's difficult to see how many moles of hydroxide we would have to add in order to use up all the acetic acid. And in an acid-base titration or many other types of titrations, this is where an indicator comes in. When you design a titration, you have to add something additional to the reaction mixture so that you can spot the endpoint, the volume of titrant that you had to add to get a complete reaction with the analyte. And that titration endpoint is typically indicated through a color change, a change in solution potential if you're measuring the potential or the current in the reaction mixture with an electrical probe, or the cessation of a precipitation reaction. So there are many ways to spot an endpoint in a titration, and it's worth pointing out here that there are actually many more types of titrations than simply acid-base titrations, but the indicator is maybe the most obvious example of how we can add one additional chemical to the matrix where the chemical reaction is occurring, which will allow us to see the endpoint of this reaction without interfering with the reaction. In addition to acid-base titrations, you can use similar titration setups to establish the concentrations of other types of analytes, including metal ions in particular. These types of titrations are known as complexometric titrations. You can run titrations based on redox reactions. You can run potentiometric titrations where you measure the current or the voltage in the reaction mixture as the reaction is occurring. So there are many types of titrations that are out there. We won't cover all of these in a lot of detail in quantitative analysis. We will make some time towards the middle of the term to talk about complexometric titrations in detail and potentiometric titrations in detail. But just bear in mind that there are other titrations that are out there, and while the experimental technique that you use to spot their endpoint may change from titration to titration, they all obey the same basic rules, and they're all about figuring out how many moles of the reagent that's present in the titrant solution you had to add to completely react all the analyte that was there originally. All right, so what I mostly want to remind you of is in the titration setup that you've seen before, what are the roles of each solution, and vocabulary-wise, which solution am I indicating if I use a term like titrant? So you may remember from titrations that you've done before, you typically take an aliquot, a small volume of an unknown solution. In your previous acid-base titrations, in high school chemistry labs or general chemistry labs, that's likely been a specific volume of a solution of a weak acid. So in those cases, your weak acid solution was the sample, and the goal of the titration was to determine how many moles of the weak acid you had in this volume of the sample, and then you could do moles over volume to establish the concentration. If we're talking about the titration of acetic acid with sodium hydroxide, our weak acid is our analyte, and we want to establish the concentration of the acetic acid. We're using the hydroxide to do it, and so in terms of our analytical chemistry vocabulary terms, acetic acid is the analyte, hydroxide is the reagent that's in the titrant solution. For the titration setup, after adding the acid and often adding a stir bar, you add a few drops of a separate weak acid, which is known as an indicator. And an indicator is a weak acid that has a very low Ka value, typically, and a very high pKa value. So it doesn't participate directly in the titration to any real extent. But the key thing is, at a pH which will indicate when the reaction is complete, the indicator will change color either from colorless to pink in the case of phenolphthalein, or red to yellow in the case of something like methyl red. But the idea is there's only a couple drops of the indicator present in order to help you visualize the endpoint, where the endpoint is defined as the volume of the titrant that you have to add to get a complete reaction. Your titrant, prior to starting the titration, is loaded into the burette, where you make an initial volume reading to determine how much solution is in the burette to start with. Then you begin to drain it quickly at first, then dropwise as you get close to the endpoint, with the idea of inducing just a very faint color change to get a good endpoint. And at that point, you stop running the solution, you stop running the titrant out of the burette. You make a note of the volume difference before and after, and you determine how much volume of the titrant solution you added to flip the indicator color. And that volume of titrant solution added is what we would call the endpoint. So in terms of the roles that are played in a titration, the solution that is in the burette is a solution of known concentration. In an analytical chemistry experiment, it should be very clearly established and accurately established what the concentration of that titrant solution is. That's something we'll come back to in a little bit when we talk about standardization. And then the endpoint is the volume of titrant delivered to the flask below the burette in order to cause a color change in the indicator. So an indicator is a compound, usually it's a weak organic acid, that changes properties abruptly when the reaction is complete. What that means in practice is the pH of the solution is such that the weak organic acid that is the indicator gets deprotonated itself, which changes its color. We'll talk more about indicators when we get to buffer actions and weak acid, strong base titrations later on in the term. The endpoint is the empirical evidence that the equivalence point has been reached. So that's the volume of the titrant that you had to add in order to change the indicator's color. It doesn't always have to be a change in indicator color, but it has to be marked by a sudden change in the solution's physical properties. Could be color, could be solution potential, could be a number of different variables. In practice, though, I'd like to point out that when we do a titration in the lab, all we can measure is the endpoint. What we're actually trying to determine is a theoretical point called the equivalence point, where we've added exactly the required moles of the reagent that's present in the titrant solution to react with all the analyte that we had in the original unknown. So in the case of an acid-base reaction like between acetic acid and hydroxide, where the stoichiometry is 1:1, if we added the exact number of moles of hydroxide that we needed to deprotonate all of this acetic acid, we would have reached the equivalence point. And that's really what we want to determine in order to establish the analyte's concentration. However, in any real-world titration, your indicator doesn't really trip until you're just a teeny tiny, very small infinitesimal amount of extra titrant added beyond the equivalence point. And so as a result, we refer to the volume of titrant that it takes to change the solution color as the endpoint, not the equivalence point. So an equivalence point is a theoretical property of an acid-base titration where we'd have equal number of moles of acid and equal number of moles of base added. In practice, we can't measure that. We can only measure a volume slightly past that, slightly larger than that equivalence point, and so we call that the endpoint. For now, if you want to think about endpoint and equivalence point as being equivalent terms, that's fine. As you get into the lab, your instructors are going to point out that equivalence point is something that we're looking for, but we can't actually measure, and the endpoint is as close as we can get in the real world. And so we base our calculations on the endpoint volume, not the equivalence point volume. As a result, though, this is another potential source of error, even in an expertly run titration. There's an unavoidable titration error associated between how much base we had to add to trip the indicator versus how much base we had to add to completely deprotonate the original acid. This difference is small, but it is present and it can make a difference. Therefore, even well-designed titrations always carry some amount of unavoidable titration error associated with their execution. And so if you were to track the progress on a titration curve, you probably saw some titration curves back in general chemistry, but it also may have been a while since you pulled one out. A titration curve measures the pH of the solution as a function of the volume of the titrant added. And so for a typical strong acid, strong base titration, you would see a sigmoid curve like this, where ideally in the middle of this steep rise section right here, you would have the equivalence point in the exact middle. Just a little bit past that, very, very small amount of volume of titrant added past that would be the endpoint, and that's what we can actually measure in the experiment. So if that helps you visualize the difference between endpoint and equivalence point, which I hope it does, that's why we're looking at this titration curve right here. You don't need to be a detailed expert on titration curves again yet. That's something that, again, we'll get to in a lot more detail when we talk about acid-base reactions, buffers, and acid-base titration specifically in more detail about a month down the line. So the next thing that I want to go over with you guys is I want to remind you how we use the titration data available from a classical titration setup to calculate the concentration of the analyte. And in any classical titration, you really only have one data point at the end of the day, which is the equivalence point volume for every trial that you did. And the other pieces of information that you have at your fingertips are the concentration of the titrant and the volume of the original unknown. You use these three pieces of data in conjunction with a balanced chemical equation like this to determine the concentration of the original analyte, and that's what we'll look at in our first worked example.